Can everyone hear me? All right, well, welcome everyone to 60 Minutes in Space. And how many of you are here for the very first time for this event? Okay, that's pretty much most of the crowd, so welcome. This is a monthly program, and what we do is we, meaning I, talk about some of the big news, space news stories from the past month. And so I usually don't go back more than the beginning of the month, but since I'm an astronomer, I tend to cover things outside of our solar system, although as you will see, we will be also talking about things inside of our solar system, especially with a big launch that you might have heard about that happened just a couple weeks ago. And if you have a really burning question, feel free to wave your arms to get my attention. But otherwise, I'll be happy to take questions at the end after we're done. Okay. So again, my name is Chun Yu, and I'm also want to say hello to everyone who's watching on Zoom. And firstly, this will be our last hybrid event where we'll be viewing, or where you'll be able to see 60 Minutes in Space virtually next year in January. I think we'll be going to only in-person events. So hopefully I will see as many people as possible in person next year. So with that, I'm going to get started. All right, thank you, everyone. So what I want to talk about tonight, the first several stories actually have to do with the James Webb Space Telescope, because obviously James Webb has been in the news quite a bit with the release of a lot of images that you might have seen or heard about since this past summer. And I just want to go through some of the new pictures and objects that have come out from James Webb since the last time I talked about it from our previous 60 Minutes in Space. And so oftentimes, we see spectacular galaxies and distant galaxies and star-forming regions from James Webb. And today I'm going to talk about locations that are closer to home, at least in our galaxy. So there's this star Hipparcos 65426, which was imaged by James Webb. And this star is notable because it has a massive planet in orbit around it. And it's in orbit, this is a star that's about 350 light years away. And what James Webb was able to do was, it was actually able to take a picture of the planet. And so these are 4 different images of the same planet at different wavelengths. And so James Webb looks at the infrared light coming from objects in space. And in this case, it's looking at 4 different near and mid-infrared wavelengths. And the star is actually located where this star symbol is. And the reason why James Webb is able to actually see this planet, normally stars are so bright, even in the infrared, they can be tens of millions of times brighter than the planets that orbit them. In visible light, the light that our eyes are sensitive to, planets can be billions of times dimmer than the star. But the James Webb Space Telescope actually has an instrument on it that can block out the central light from the star. And so here you're seeing the light basically reduced to almost nothing by this instrument called a coronagraph. And after they did that and did additional processing to subtract out residual light, they were able to basically image this planet. And this planet is actually orbiting about twice the distance that Pluto or Neptune orbits our sun. So it's actually pretty far away, but because it's a big Jupiter, multi-Jupiter-sized planet, and it's relatively young, it still has a lot of heat of formation, and so it's glowing in the infrared. And you might also notice that these the images look kind of weird. And that's just because as light goes through the optics system on the James Webb Space Telescope, point sources get modified. And so in this picture here, you notice that stars have these, what astronomers call diffraction spikes. Notice these cross patterns. And those patterns are unique to every single telescope. And what happens is as the light bounces through the mirrors in a telescope, it picks up this unique pattern. So for point sources and all stars, they're so far away that they appear as single points of light. The point sources pick up these diffraction patterns. And so what's happening here is that we're seeing elements of those diffraction patterns, and they're slightly different depending on the wavelength. And so that's why you're seeing slightly different images depending on what wavelength or what color of the infrared you're looking at. All right, so here is another image that was released in the past month or so. And this is much, much closer to home. Does anyone have a guess? If you haven't seen it, any guesses as to what planet we're looking at? There's obviously a planet here. Yes, ma'am. Neptune, yes, that's absolutely correct. And before we zoom into Neptune, notice these spikes that are around the stars. And notice how they're different from the diffraction spikes that we saw in the previous slide. So this is what stars or single points of light look like when they're imaged by James Webb. And so as the light goes through, bounces off the different mirrors, it actually picks up this weird sort of six-pointed, actually 8-pointed pattern. And that's just, again, a factor of the telescope that's doing the observing. So what we're going to do now is we're going to zoom in to this view. And here is Neptune. And this is actually Neptune's moon, Triton. And it appears super bright because Neptune is far away enough that it's very cold, far from the sun. And there's nitrogen snow on the surface of Triton. And so that makes it very, very reflective. It's about, I think, about 70% reflective, meaning 70% of the light that falls on it gets reflected back into space. And here is Neptune, which we'll see a picture of what it looks like in visible wavelengths. And here, these labels identify some of Neptune's moons, along with, obviously, we can see the rings around Neptune. Most people know that Saturn, the planet Saturn has rings, but actually all the giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, also have rings. And we're also seeing bands of clouds in Neptune's atmosphere. And here's a comparison of what Neptune looks like. So here is the Hubble Space Telescope view. And you can see that Webb, in this case, has done a better job than Hubble, or pretty comparable. But it's definitely seeing details at these wavelengths that are difficult to make out in visible light, especially the rings. And of course, the best picture that we have of Neptune comes from a spacecraft that flew past it more than 3 decades ago. So that's the Voyager 2 spacecraft. And it was able to give us really high resolution imagery. But since we don't have any plans to fly any spacecraft to Neptune in the near future, that means James Webb and Hubble, those telescopes are it as far as getting us good views. Here is two James Webb Space Telescope views of Mars. And what we're looking at is a portion of Mars that's focused on something called the Halus Basin. And this is a giant impact basin, meaning an asteroid, a large body smashed into Mars. And this is, you can see that it's round. This is about 1,200 miles across. And it basically created a gigantic crater. And of course, Mars is covered with lots of other craters. And what we see in this image, this is at a wavelength of 2 microns. And this is what astronomers call the near infrared. So this is just slightly past the the visible part of the spectrum, so past the red. And what we're mostly seeing is reflected light. So sunlight contains infrared radiation, and that radiation is bouncing off of the surface. And so you can see that this infrared image looks pretty similar as far as the dark and light regions as this visible light image. And so what we're seeing are basically distributions of dust on the surface of Mars. So Mars is very dusty. There's darker dust as well as lighter dust. And so this reflected infrared light basically looks like the visible image just because the dust is reflecting that light in the same way. Now, James Webb is also looking further into the infrared, what they call the mid-infrared. And in this case, this looks very different. And what's happening here is that we're seeing the part of the Martian surface that's most heated by the sun. And so you can imagine the sun is directly shining over the spot. And so this spot is the warmest, and it gets cooler as you get further and further away from that, what they call the subsolar point. And the Hipparcos Basin also shows up as a darker spot. And we think we're seeing it that way because this is a depression. It's actually a big bowl on the Martian surface. So we're looking deeper into the atmosphere. We're looking through more carbon dioxide. The Martian atmosphere is more than 90% CO2 or carbon dioxide. And so that results in this kind of darker looking spot. And one of the things that you can also do with telescopes is to spread out the light. So instead of just taking a picture, you take the light and you spread it out. And when you do that, you can actually get basically a fingerprint of all the elements of the molecules and different compounds in the atmosphere. So in this case, they did that with the Mars observations. And again, if you know how different molecules, whether it's carbon dioxide or water or carbon monoxide, how they absorb infrared light at different wavelengths, you can actually read these fingerprints. And so you can basically figure out what the makeup of the atmosphere is. And how these lines show up depends on the temperature, the pressure, lots of different variables. And so by carefully studying this, astronomers, planetary scientists can actually gain a lot of information about the Martian atmosphere. All right, so I'm going to go ahead and we're going to move on to some stars that are a bit further out from our solar system, although they're still pretty close, galactically speaking. They're well within our solar neighborhood. And what I want to do is orient everyone. And if you go out and tonight or in the next couple months, you'll see familiar winter constellations. So Orion is a very easy to spot constellation in the winter sky if you look towards the south after sunset, because it has these three belt stars. And we think of Orion as being this great hunter with a shield and either a club fighting off or attacking some wild animal. And he has a sword that hangs from underneath his belt. And if you see Orion and look off to the right of it, you'll see the constellation of Taurus, the bull. And Taurus is really recognizable by, there's a red star called Aldebaran that makes up the eye of the bull. And if you look carefully, especially if you're in a dark enough spot, so away from street lights, you might be able to see the horns of the bull. And the Taurus has really big horns and a really small body. And then above the bull is a small cluster of stars known as the Pleiades. This is also a very famous grouping of stars. And so these are all stars and constellations that you can see if you went out tonight after this talk and through the next couple months. And here is an image built up of multiple telescopic images of Taurus and the Pleiades. So the Pleiades, they're also known as the Seven Sisters, famously from Greek mythology, is up here. And then here, again, we see the head of the bull. And so you have the head, and then the horns of the bull come out this way. This is that star Aldebaran I was talking about earlier, this reddish giant star. And what we're going to do is we're going to successively zoom in. So we're going to zoom into a part of the sky that doesn't look like much. It doesn't look like there's much there. And we're going to keep zooming in so you can see some of those stars look familiar. And now we're going to zoom in even further. Again, it doesn't look to be much here. There doesn't seem to be very many stars. You can use this grouping of stars to sort of orient yourself. So that's these stars. And now we're going to zoom in again slightly near the center. And you might notice, oops, there's a kind of a fuzzy patch. And maybe we can turn off the stage lights so we can see this a little bit better, because I know this looks really faint, especially for people in the back. Okay, let's shut off the stage lights. There we go. All right, can people see it better now? So there's this little fuzzy thing, and it's completely surrounded by black. So there doesn't seem to be many stars. But you might even notice that, there seem to be stars around it, but there's this big hole in the sky where there aren't many stars at all. And that's a clue to what we're seeing. And now let's zoom in all the way. And now, we've changed the exposure so that we're seeing even some of the dimmer stars. But there's this kind of fuzzy patch in the sky. And it turns out that there are stars in this direction in the sky. But those stars are hidden. And the reason why they're hidden is that space, in addition to containing stars, also contains lots of gas and dust. And it's these gas and dust that collect together into gigantic, massive clouds. And the reason why we don't see very many stars is that we're actually looking towards where there are these gigantic clouds of molecular gas. And I call it molecular gas because most of the universe is hydrogen. But it turns out that these clouds are so cold that the hydrogen atoms bond together to form what we call molecular hydrogen. So two hydrogen atoms pair up to form H2, or molecular hydrogen. And so these gas clouds are normally very difficult to see because they block the starlight coming from around them. But what you can do, and a lot of amateur astrophotographers have done this, is they take extremely long exposures, so leaving their camera or telescopes and with their digital sensors open for many tens of minutes, sometimes even hours. And what they can get are spectacular images like this. And so this is pretty much the same part of the sky that we were looking at before. So here are the Pleiades again, the Seven Sisters. Here's Aldebaran. Here's the head, that triangular head of Taurus the bull. So you can imagine the horns coming off in this direction. But with this really long exposure, you can see that we see lots more stars, thousands, hundreds of thousands, maybe millions of stars. But you also notice all this kind of brownish, blackish material that look like clouds. And so these are the molecular clouds I was talking about, how gas in interstellar space can basically aggregate by gravity. So they get concentrated into these clouds. And you can see that parts of the clouds where the gas is denser, there's more gas, it's actually darker or blacker. And that's because the denser parts of these clouds block more of the light. So when you look at kind of these brownish sections, they're not as dense, they're not as thick, and so you start seeing more starlight poking through. But when you look at the very cores of these clouds, these deep sections here, very little starlight pokes through. And that's because these clouds are so thick or so dense. And so what we're going to do now is we're going to concentrate on these set of clouds here. And these are known as the Taurus clouds. And they're located about 450, 460 light years away. It turns out that the Pleiades are a little bit closer, they're about 400 light years. Aldebaran turns out to be the closest major object in this picture. It's only about 65 light years. So we're seeing light that left Aldebaran. If you went out and looked at Aldebaran right now, that light left how long ago? 65 years, and so that would be like the late 50s. So that's when that light left, and we're seeing it now. All right, so we're going to concentrate on this section here, and this is from another astrophotographer who goes by the name Old Eyes, and so I grabbed it from this website. And so now we've kind of reoriented the image so you can see those clouds again. And all these Bs correspond to a catalog by an astronomer named Barnard, who mapped the sky, and he counted these dark regions. And so that's what these Bs correspond to. But that fuzzy patch that we were looking at earlier is actually right here. So it's actually located right in the midst of this clump of clouds. You can see that there are lots of other clouds, but this is the one that we're headed towards. And we can turn this off. So you can see, remember that, that fuzz that looked kind of triangular? Well, that's it right there. And so it seems to be breaking out of this cloud. And in fact, that is exactly what's going on. So let's go back to this image again. We've zoomed out a bit so you can see that fuzzy patch. And then here is the same part of the sky, but looking at it in the infrared with a ground-based telescope. And this shows you how different the sky can look in visible light, which is the light that our eyes are sensitive to, versus infrared. And so what happens is that infrared light can actually pass through a lot of that obscuration, a lot of that those dust and gas clouds that we were talking about. And that's why you see many more stars in this direction in the, what this is called the near infrared, than you could in the visible light that that our eyes are, that we've evolved to see. And so now we're going to zoom in again, and now we're going to look at this in from the Spitzer Space Telescope. And so this is even further into the infrared. And so the further you get into the infrared, the more this cloud is transparent. And so at these particular wavelengths, you can see that it's not just one sort of triangle, it's actually two triangular blobs. And then there's dark regions on either side. And so what is going on here? Well, it turns out that there is a young star that's being born right at the center of this nebula, this kind of butterfly, astronomers call this bipolar nebula. And so what's happening is that these clouds contain the building blocks of stars and solar systems. And so the gas and the dust from the cloud is actually falling in gravitationally, being pulled towards that very young star, and it's accreting, or that gas is falling in and building up that star. But at the same time, and this is something that astronomers were surprised by when they first discovered this, but it turns out that in addition to stuff falling in, stuff also gets shot out. And so it turns out that material piles up in the accretion disk around this young star, and a lot of it actually gets ejected out along the north and south poles. So you can think of this as the equator, and the north and south poles are in these two directions, off to the left and right. And so as the gas gets ejected in a wind or in a jet, that material basically carves out a hole or two holes in the molecular cloud. And so we're seeing this process of star formation. Not only is the star building up, but it's also destroying the cloud from the inside out. And so this is a model of what this system looks like. So there's a central protostar. There's what we call an accretion disk, where the material, the gas and dust that's fallen in from this outer envelope piles up and slowly spirals in. And then at the same time, there's a wind or jets that shoot out along the polar directions. That's why we call it a bipolar flow. And it carves out not only a big cavity, but they also get a sense that there's a small inner cavity that you can sort of get a sense here, that there's two smaller holes that are closer into the star that are slightly different in geometry compared to kind of this big voids that have been carved out. All right, so this is work that, so this is from a paper that was published in 2008. So this area, this region of the sky has been of interest to astronomers for a long time. And there has been a lot of speculation as to what could have caused that young protostar to carve out an inner and an outer cavity. And so you'll see this reference as a neck because it's different than, this inner region is different than the outer region. So they either call it a double cavity or a double or a neck. And so one idea is that the star has a wind that's expanding outwards, but because there's material falling in from all directions, the wind from the star gets redirected. So there's a lot of gas near the equator, and so it's hard for the wind to push out along the equatorial direction, and so it gets pushed out towards the poles. And then what happens is just from how fast this wind is blowing from that central star and how dense the gas is, you can actually get kind of a narrow neck towards the center and then a much bigger cavity out at the edges. Another idea is that if you, instead of just a single star, perhaps there are two stars at the center. So it's a binary pair. And what happens is these binary pairs, they orbit one another, but they can also pull in gas from the surrounding cloud, and that can also carve different sized cavities. And finally, there's also this idea that perhaps, and this is from a completely different object. This is from a young star called Alias 29, but they see evidence of a powerful jet. See, you see this here. And then also these blobs off at a distance. And this jet is precessing, meaning what's happening is that it's actually spinning as it's shooting out. Sort of like if you had a garden hose and you're spraying water, if you pivoted or swung the end of that garden hose around, you would get material that would shoot out in different directions. So there's, and so you can see not only the jet here, but you can see the jet smashing into gas in the cloud and lighting it up. And so this is another way in which these jets can basically carve out different size cavities in the gas. So whether any of these ideas are correct or whether there's another idea that's ultimately the correct explanation for what we're seeing, we're still not quite sure, but the new James Webb Space Telescope observations that just recently came out in the last couple of weeks of this region may help astronomers figure this puzzle out. So again, this is the Spitzer Space Telescope view of this region, and I'm going to show you what the James Webb Space Telescope image looks like. And so this gives you a sense of just how much more detail we're seeing with this amazing telescope. So again, we're looking in the near and mid-infrared. So that allows us to basically look through a lot of that obscuring gas and dust. So again, you see the two sort of butterfly-shaped cavities. And the way these colors are set up, so there are actually 4 different colors that are used to render, to make this image. And obviously, our eyes can see blues, greens, reds, and oranges. But what astronomers have done is they've taken the infrared information at different wavelengths, and they've remapped it, basically retranslated it into visual information that our eyes can make sense of. So that's what these colors represent. They represent different infrared wavelengths. And what's happening is that the bluer the light, the less obscuration we're seeing. And so it turns out that at this particular wavelength, you can only go through so much of the cloud. And as you go to green and red and then orange, you're seeing thicker and thicker layers, or seeing through thicker and thicker layers of the cloud. And so so this basically corresponds roughly, maybe out here to that faint fuzzy patch that we first saw, 10 minutes ago in optical wavelengths. And then as we go to greens and reds, we're seeing deeper into the cloud through more obscuring gas and dust. And then finally, the orange parts are the ones that are the deepest or the most obscured. So let's zoom in. And so what's amazing about this is that we can really see that accretion disk that people have postulated. So basically all the gas from the cloud is falling in. It's being pulled gravitationally by that young star, and it's piling up into this accretion disk. You can think of it as sort of like a big dinner plate or a big pizza, something that's big and flat and round. And that gas spirals in, and then that young star sends much of that gas shooting back out to form, to carve out these giant cavities. And we'll just look at some other close-ups of this. So this just gives you a sense of just how complicated these regions are. So these, they're not nice, smooth bowls that we saw in that cartoon model a few minutes ago. The different parts of the cloud have different densities, and so the material doesn't carve out a nice, smooth surface. It becomes very irregular. And then on the other side, you kind of get the same sense that this is a very complicated region that people will be studying for a long time. Right, so let's go on and talk about another planetary system. And this is not a young star. Is there a question?
Yeah. Is it okay to ask?
Yeah.
On that, I always hear about gas and dust atmosphere in these enormous distances.
Mm-hmm.
How thick is it? I mean, is it like there's a speck of dust, and then you go 100 miles, there's another speck?
Yeah, so
you know what I mean?
yeah, so that's a great question. What do we mean when we say, we're seeing lots of gas and dust? Is there a speck of dust, in one location, and instantly, a mile later you find another speck? Well, in our atmosphere, I think I'm trying to remember the numbers, but within like a single cubic centimeter or a cubic inch, there's typically on the order of maybe 200 billion particles. So that's basically a 2 followed by 20 zeros. So that's a really big number. That's how much gas atoms, molecules there are in a little tiny cube in our atmosphere. When you go to interstellar space, where there aren't any clouds, you might find 1 or less than 10 atoms or molecules in a cubic centimeter. And when you get to these gas clouds, on average, you might get maybe 10,000 particles per cubic centimeter. And as you get to denser and denser regions, the numbers start going up. So it could be a million, it could be 100 million, billions, and so forth. And until at the very centers of these clouds, they're still very much vacuums in the sense that they're many, many orders of magnitudes less dense than our atmosphere. But there's sufficient enough material, and because we're looking at distances of, these clouds can be light years across, so they're vast, conglomerations of gas. And even in this region, we're seeing things that are multiple sizes of our solar system. So maybe 100 times the size of the orbit of Neptune is. I'd have to work it out, but that's roughly. This is probably hundreds of times the size of our solar system, and so that means the light has to travel, through vast distances, and there are lots of opportunities for the light to be scattered or to be absorbed by the dust or the gas molecules. So even though, if you were to take a sample of this gas and bring it to Earth, it would be very similar to a vacuum because it's still not very dense, because this distances are so vast in space. It can still lead you, to give us these very spectacular images where it looks like we're seeing these thick nebulous features. But thank you for that question. So let's, as I said, I'm going to talk about this new observations of a planet around the star WASP 39. And the way that astronomers name planets is the very first planet that's discovered around a star outside of our solar system. It gets the name of the star, but there's a b, a lowercase b attached to it. So the lowercase a is actually the original star itself, and each new object that's discovered around that star is a b, and then a c, and then a d, and so forth. And so WASP 39b is, there were some new observations used in the James Webb Space Telescope. But before I get into the James Webb observations, I just want to talk about how planets are discovered. And so again, stars, they're so far away that even in our best telescopes, they appear as single points of light. And planets, because they can be up to 10 billion times dimmer than the star, they're very, very difficult to observe. So it's almost hopeless to try and take a picture of a planet unless you use some very specialized techniques. And so this is what astronomers do. What they look for, and this is one of the most common methods for detecting planets, is this is called the transit method. And they look for solar systems where the orbits of the planets are basically lined up to be along our line of sight. So let's go back and watch this again. And so if a planet's orbit crosses the star, and if you watch the star, you'll see a slight dip in the brightness of the star over time. And if you have a larger planet, it's going to create a bigger dip because more of that planet will be eclipsing or blocking the light from the star. And so a transit is basically something crossing in front of something else. And for the sizes of planets relative to their stars, the amount of difference or the change in light is typically less than 1%. Usually a lot less, a lot smaller than 1%. But astronomers first started doing this on the ground with the ground-based telescopes more than 25 years ago, and now we have satellites in space that have allowed us to discover thousands of planets, and you can use the James Webb Space Telescope to do the same thing. Now, once you've discovered that planet, you can actually start making additional discoveries about that planetary system or about the planet itself. And one of them is the fact that depending on the wavelength of light that you're observing, the planet might actually look or appear to be different sizes. And here we can see that. So this planet is shown in green and purple and brown. And depending on the particular wavelength you're looking at, the green planet, or observed at the green wavelength, is smaller than how the planet looks at the purple wavelength, and it's smaller still compared to this orange color representing this third wavelength. And what we're seeing are the effects of different molecules in the atmosphere of the planet. So we have molecules like carbon dioxide or methane or other gases that those gases can block light coming from the star. And so particular wavelengths of light might be less transparent or more opaque in that atmosphere. And so as a result, depending on the wavelength you're looking at and depending on what the atmosphere is made up of, the planet will actually look to be of different sizes, and as a result, the amount of light that's blocked will change. And even when the drop in the light occurs, so you can imagine that at the 2.3 microns, this orange view of the planet, that because this is bigger, this will start blocking the star's light sooner than the 2.1 micron, the green view of the planet. And so in this case, you can see this light dropping sooner than over here. And of course, the depth is also larger here than here, just because the area of the planet is larger. And so we can basically use this information to tell us the composition of the atmosphere of these planets, because we know that different wavelengths of light can be associated with different molecular species. And this is what this team of astronomers have done with WASP 39b. So here is WASP 39b. Again, this is, we don't have the technology to take pictures of planets, so this is just an artist's rendering. But this is an object that's about 700 light years away. And it's a gas giant like Jupiter or Saturn. And in fact, it's actually very close to the mass of Saturn. So we think that it's about 0.28 Jupiters in mass. And Saturn is about a third of a Jupiter, so it could be slightly smaller than Saturn. But notice how big it is. So the planet radius is more than 1.25 times the size of Jupiter, and Jupiter's our largest planet. And so this planet is puffed up compared to the Saturn or Jupiter in our solar system, and I'll explain why in just a second. And also notice how close it's orbiting the star. So this AU is an astronomical unit, and that represents the distance between the sun and the Earth, so which is 1. So this is less than 5% the distance between the sun and the Earth. And in fact, that's also a much smaller distance than the distance to Mercury and the sun. And it goes around its star in 4 days. So its year is basically 4 days long. It's whipping by really quickly. And so here is a 2-scale diagram of showing how close this planet is compared to its parent star. And so the reason why this planet is puffed up, it's much bigger in size than our planet Jupiter in our solar system, is because it's so close. The parent star in this system is heating up the atmosphere of WASP 39b and basically causing it to grow much bigger. And then here is a comparison of the WASP 39 system. So here's WASP 39, and here is WASP 39b, and here is the orbit of Mercury, Venus, Earth, and Mars by comparison. So you can see that this solar system is much, much smaller than our own because this planet orbits a lot closer. So like I said, astronomers use James Webb to measure the light coming from the star during one of these transits, actually during multiple transits. And this is that effect that I was talking about, how at different wavelengths, the transits are different, so that there are different depths of transits, and there are different times of when the transit actually occurs. So you can see how at different wavelengths or different colors in the infrared, you're seeing slightly different transit information. And from this, we can basically reconstruct what astronomers call a spectrum, which is taking all the light from that star and then figuring out what the contributions from the planet are. Because the light has to pass through the atmosphere of the star, and if you subtract out the effect of the star, you can basically get the effect from the atmosphere of the planet. And so these points with the vertical error bars, the gray points, are the actual observations from the James Webb Space Telescope. So you can see that it's very noisy and very complicated. But what they've drawn in colored lines are computer models of what the atmosphere must be like. And so the black line is the most accurate one that seems to fit these points the best. And these different colored lines are basically taking the best model fit and then removing certain molecules. And so if they don't have clouds in the atmosphere, they have this kind of purplish blue line. If they don't have methane, there's this other line that's not as accurate of a fit, and so forth. And so basically by just playing around with different parameters, different amounts of different gases, they can try to create a model for the atmosphere that fits the data the best. And so this is what they've done for different instruments in different parts of the infrared part of the spectrum. And here they identified, and it's kind of hard because it's very pixelated, but you can see that there's water, there's carbon monoxide, there's even potassium, and then there's also something here, it's barely readable, that's sulfur dioxide. So these are features that are caused by specific molecules in the atmosphere of this planet. And yes, a quick question. Yeah, how can it have water if it's so close to its star? Well, the water is not liquid, so it's actually just in a gas phase. So you think of the water as having been heated up so much that it's in the atmosphere, sort of like steam. And because this is a very massive planet, its gravity is also much stronger, and so it can hold on to its gases better than if it was on, let's say, an Earth-sized planet. But that's a great question. All right, so it turns out that the sulfur dioxide was a completely surprising discovery because they didn't expect sulfur dioxide at all. And in fact, they had to go back to the drawing boards and kind of figure out exactly how sulfur dioxide could be formed in the atmosphere. And it turns out that there is a way where you require ultraviolet radiation from that parent star to break up water molecules and this H2S, hydrogen sulfide, that we think does exist in the atmosphere. And through this complicated process, you can form sulfur dioxide. And then after the discovery of the sulfur dioxide, they were then also able to talk about what additional heavier elements or what fraction of heavier elements must there be for them to get this much sulfur dioxide. So it turns out that the best fit is where you have about 10 times the amount of heavy elements that we find in our sun. So basically by looking at this light very carefully and by using computer models and by understanding the physics of how light interacts with these molecules in the atmosphere, you can actually learn, as we see, quite a bit about the composition of the atmosphere. And so this is an important test for how astronomers can use telescopes like James Webb to study, and to look for signs of life in other planets. All right, so I'm going to end tonight by talking about the Artemis 1 launch. And I'm going to, since we're running up on 8 o'clock, I'm going to go through this really quickly. But this launch occurred just 2 weeks ago. So on the night of November 16th or 15th, if you're here in Colorado, about 13 minutes before midnight, the Artemis 1 rocket launched. And This rocket is designed, well, it basically sent a spacecraft to the moon, and it's useful to sort of compare it to our previous big rockets. So the rockets that we actually did send humans, American astronauts to the moon, was the Saturn V, which was about 363 feet high. So you can see that the Artemis 1 is just a little bit smaller, but it turns out it provides more thrust than the Saturn V. And then the other rocket that people are familiar with is the Space Shuttle, which stopped flying in 2011. But it turns out that there's a lot of similarities between the Space Shuttle and Artemis. So if you look, you can see that the Space Shuttle has an external fuel tank, which contains the fuel that's burned by the Space Shuttle engines. And it also has these two solid rocket boosters, which fall off after launch. And basically, this main core here is based on the external fuel tank. So it's basically the same size, but it's a lot longer. So it's the same diameter. And the engines at the bottom in this main core stage are in fact Space Shuttle engines. So they're basically spare engines that were built but never flown on a shuttle. And the solid rocket boosters on Artemis are again very similar, if not almost exactly the same, or they look almost exactly the same, except there are four kind of rings or stages to the shuttle's boosters, and here there are 5. So they're basically taking a lot of shuttle technology and updating it for Artemis. So here is, again, the Artemis spacecraft or rocket, and here's that core stage built on the external fuel tank. Here are the 2 solid rocket boosters. Here is the Orion crew module. So that's the one where when we do send astronauts on board this, that's where they will be. There's the top part of this is called the Orion spacecraft. This whole thing is the Artemis 1 rocket, and they also tend to call just the launch part the space launch system. And here we are blowing up the core stages, or the core stage, and again you can sort of see how this is very similar to the external fuel tank, where we have a big tank for the liquid hydrogen and a slightly smaller tank for the liquid oxygen, and both of those are required to burn in the space shuttle engines at the bottom. And then here are the solid rocket boosters, and again there are 5 segments to this. So again, built on the shuttle model, but making it slightly longer. There's also what's called the cryogenic, or the interim cryogenic propulsion stage. And so that's basically the stage below Orion, and that's used after this lower stage drops off. And so there's an additional stage that has liquid hydrogen and liquid oxygen inside that turns on after the main core drops off. And finally, here is the Orion. And so here again is the capsule where the humans are kept alive. There's also a service module that contains fuel tanks and lots of other equipment to support the crew module. There's a launch abort system, so if something goes wrong, this is actually a rocket that can pull the capsule away from the rest of the rocket, so to save the astronauts' lives. And then there's also an additional stage below this that's used for maneuvering, and this is actually built by the European Space Agency. And so this Artemis launch didn't have any humans on board, no astronauts, but they did have 2 mannequins, and what they're put on to basically help study the effects of the launch on future astronauts. And so there are radiation monitors to measure how much radiation they're receiving, and they also one of them is wearing a special radiation vest. And so they're testing this to see how effective this will be for astronauts who go on the next Artemis flight. And another big test of Artemis is to test the heat shield. So it turns out that when the Orion spacecraft comes back to return home to Earth, it's coming back at about 25,000 miles per hour. So this is actually a lot faster than spacecraft that are returning from the International Space Station or even the Apollo missions. And so they want to test to see how well the heat shield holds up when it's traveling into our atmosphere. All right, so with that, let's take a look at the launch. So this has occurred just before midnight our time.
Sound suppressor water now flowing
15.
under the ML. And here we go.
10.
Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
All 4 RS-25 engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour. Hearing good control on the roll from teams in Mission Control Houston. All good calls so far. Now 30 seconds into the flight of Artemis 1. First milestone will be for the vehicle to pass through max Q at about 1 minute and 9 seconds into launch. This is the greatest period of atmospheric force on the rocket.
We're going to see the solid rocket
You're looking at
boosters
8.8 million pounds of maximum
separate
thrust.
next.
Quiet here in the loops in Mission Control. The 4 core stage engines are throttling down ahead of passing through max Q. Standing by for solid rocket booster jettison and shortly thereafter.
And unlike the shuttle, where they save
Confirmation that the solid rocket boosters have separated these 177-foot boosters. Now the core stage continues to power the flight of Orion, all 4 RS-25 engines firing, traveling over 3,400 miles per hour, 46 miles downrange.
So unlike the shuttle solid rocket boosters, which were reused, these just land in the ocean and they're not reused at all. All right, so this is actually a really complicated diagram showing what happens after launch. So after the separation from the main core, the interim cryogenic propulsion system pushes the Orion spacecraft towards the moon. It separates, and then it goes into this complicated, what they call a distant retrograde orbit. And just to sort of explain or to visualize what this looks like, I'm going to use our Open Space Planetarium software, and we're seeing the orbit of Artemis as seen from the Earth. And so it takes a couple of days. I don't know why it's blacking out, but it takes a couple of days to get to the moon. But then it does a close rendezvous or orbital encounter with the moon to get into this outer orbit. And so seen from the Earth, you can see that Artemis is still orbiting the Earth just as the moon is, but it's also under the gravitational influence of the moon. And so because of this, it's actually in this very stable orbit where it's always in radial contact with the Earth. So in the Apollo program, the Apollo spacecraft orbited so close to the moon that when they were on the backside, they were cut off from radio communications. So this way, they're always in communications with the Earth. And then after about 25 days, they do another close encounter with the moon, and that sends them back towards the Earth. So this is the orbit from the Earth's perspective. We can also see what the orbit looks like from someone sitting on the moon or standing on the moon. And so here is kind of a lunar perspective of Artemis, and here you can see it coming into its close flyby, and that close flyby sets it up into this orbit that we saw earlier, where it was near, but also far away from the moon. And this orbit looks a lot stranger, and that's just because every time Artemis passes inside or outside of the moon's orbit, it results in this corner or this bend. And so this is just entirely an artifact of the fact that we're looking at this from the moon's perspective and not from the Earth's perspective. And finally, here is that second close flyby. And again, we're headed back towards the Earth. So you can see that during this whole time, it's staying relatively close to the moon, but again, always being visible to the Earth. All right, so with that, I'm going to just leave us on this. This is a video that was made from a camera on board Artemis. And Artemis will be in its mission for another couple of weeks before returning home. And then it will be a few more years before Artemis 2 launches, and that's the one where we have the first astronauts on board. So that's the first crewed mission. And Artemis 3 will be the one that will actually land people back on the moon. And that's not expected to take place until at least 2024. So hopefully 60 Minutes in Space will still be around to report that. So with that, I want to thank everyone who came out tonight. It is 8:01, so if you have to leave because it's a school night, feel free to take off, but I'm happy to answer people's questions. Yes? So where is Artemis right now? Artemis is actually much further away than this particular picture, and I didn't upload any pictures showing exactly where it is, but it's if you remember that first orbit with the blue line where the spacecraft was further away than the moon, I believe it's basically in that part of the orbit where it's beyond the moon's orbit, but it's still in orbit, basically around the Earth. Yeah, it's still around the Earth. So it's not at the point where it's about to head back, because we still have, I believe, at least another week and a half before it does that. Yes, sir.
Going back to the WASP that you had, the giant gas planet that's so close to the sun. Wouldn't that sun be destroying that planet because it's so close? Like the solar wind would just be stripping it away, the heat. Isn't its future rather bleak?
Yeah, that's an excellent question. In WASP 39b is so close to its parent star, wouldn't you expect the parent star, the sun, to basically be blasting it apart via the solar wind or radiation? And I haven't looked into into the details of whether how much. I mean, the fact that the planet is puffy, it's puffed up because of heating by the sun, tells you that there probably is a lot of gas escaping from the top of the atmosphere. Without studying this more, I mean, I can't tell you, how much longer we'd expect WASP 39b to last, whether it's millions of years or tens of millions of years or shorter. But there are other planetary systems that we know of where we see that the planet is so close to the parent star that we expect the planets not to survive. So there are systems, whether that we do expect the planets to be completely destroyed over time. And again, the amount of time can, might be many tens of thousands or hundreds of thousands of years. But given the lifetimes of the stars, we expect eventually the planets will be destroyed, maybe even on the order of millions of years. But I don't know exactly what the case is for WASP 39b. And Mitch, if there are any questions from the virtual audience, please let me know as well.
There are. How do people using JWST decide which stars to use the coronagraph on?
Yeah, that's an excellent question. So the coronagraph, like I mentioned before, is the instrument that allows you to block out the light of the parent star. And once you've removed that light, you can let the very faint light of the planet shine through, and then you can record that. So as far as deciding which stars or how to use the coronagraph, well, astronomers who study planets, who are looking at planets around other stars or studying planets around other stars, they probably have a big target list of stars and planets that they want to study. And the way that big telescopes like James Webb work is that astronomers actually have to write proposals. So they have to describe the science that they want to do and how they're going to do it, and and whether James Webb is even appropriate for the type of science that they want. And these proposals are reviewed by other astronomers. So it's not that anyone can just sign up for James Webb time. They have to really justify the science that they do, and only after they've gone through this review process and that the proposals that are accepted then get queued up. Their observations get queued up, and so it's really after this long process, with astronomers who have been studying these objects for a long time, and they know, which stars and which planetary systems, where the planets have to be far away enough, because if they're too close, even the coronagraph might not be helpful in removing enough light to allow the planet to shine through. And after basically justifying their observations, if they've managed to pass through all those steps, then with that review, then the people who run James Webb can then say, well, we can queue up these observations to look for these planets. And I think in the case of that particular Hipparcos system that we saw, the planet was actually discovered before James Webb, but because of the fact that James Webb is in space and because of its terrific optics and technology, it was able to observe this planet better than previous observations. Any other online questions?
Yeah. Yes, if we were inside a nebula, would our vision or line of sight be impaired at all?
Yes, I think the answer would be, depending on where you are inside a nebula. So you could be inside a molecular cloud, one of these very dense clouds. And in fact, we think that the sun in its orbit around the galaxy probably passed through molecular clouds. The sun orbits our galaxy once every about 240, 220 million years. So there are plenty of opportunities for it to go through a molecular cloud. And in that case, the stars would wink out. You might see very few stars in the sky. If you're passing through or if you're in a bright part of the nebula, so one of the parts that, let's go backwards quite a ways, like maybe this nebula here, where there is lots of energetic activity. What you see might depend on how energetic this activity is. And so there are some places where massive stars are irradiating the gas in ultraviolet radiation, and it basically heats the gas up to over 10,000 degrees Celsius, and it ionizes and basically creates a plasma, and so it basically creates a very faint glow to that gas. And so that's potentially something that you might be able to see. But again, because the gas is so diffuse, it'd be hard to see. Even though this looks like it's a bright glow, remember, we're seeing the infrared light. And so we're basically seeing heat signatures from the gas here. And so if you were to transplant yourself to this location, you might see light from the central star, but all this stuff here might not actually be visible to your eyes, because our eyes aren't sensitive to infrared. So it all depends on how much actual visible light is caused by the jets and the winds from the star impacting the gas. Yes, a question?
I hear about dark matter and black holes.
Yeah, so the question is, what about dark matter and black holes? Well, those are two completely different topics, it turns out. Black holes are the end stages of very massive stars. So stars about 8 times larger than our sun will blow up in supernova. And there are different end products to those supernova explosions. you might end up with a small compact object called a neutron star, which is basically like the leftovers of that massive star. But if the massive star is large enough, the amount of mass will keep falling inwards basically forever into a pinch point that we call a black hole. And there, we have a lot of evidence that black holes exist, not only from the result of massive stars dying, but black holes also formed early in the universe. And they, it turns out that they reside at the centers of most galaxies. They're at the center of our Milky Way galaxy. We have a black hole that's 4 million times the mass of our sun. So black holes, there are lots of black holes out there. Our Milky Way probably has tens of millions of black holes, the vast majority of which we haven't been able to observe because black holes are very difficult to observe if they're by their lonesome selves and not accreting any matter. Dark matter is something that's, again, like I said, very different. And it turns out that our universe, so we think of the universe as dominated by matter. Everything in this room, all of us, are made up of matter, protons, neutrons, electrons combine together to form atoms, atoms combine to form molecules, and then you keep building up to larger and larger things. But it turns out that the mass of the matter in the universe, at least the mass made up of matter that we're familiar with, is actually a fraction of what exists in dark matter. And so by observations of galaxy clusters and even stars in our own galaxy, we've observed gravitational effects from dark matter, even though we don't actually know what it is. And so dark matter appears to pervade our galaxies, they pervade space, and they basically probably help form galaxies from the beginning of the universe, but we still don't have a good idea of what makes up dark matter. So dark matter is so strange that it's not like you can go out and capture a bit of dark matter particle. It's still somewhat mysterious, but there are a lot of ideas as to what dark matter might be, and people are, they have a lot of theories as to what it is, and also how to determine which of these theories is correct. But right now, dark matter is still somewhat mysterious. Any other questions from our local audience or the virtual audience? All right, with that, I want to thank everyone for coming tonight. And we won't have a 60 Minutes in Space at the end of December, so we'll see everyone in January. Thanks, everyone.